ANOVA stands for Analysis of Variance. This is the basis of analyzing more than 3 treatments or more than 3 populations. You know, in the basic statistics, we learn how to make conclusion based on one sample or one population, that is using one sample t-test. Then regarding two samples or two population based on uh, two sample t-test, two sample t-test. Here, in this case, we want to make conclusions about the more than two population means, more than two population mean. In that case, we have to use ANOVA, technique called ANOVA, analysis of variance. In ANOVA, total observed variation of data. We know another name for variation is sums of square. That is total sums of square partition into different component and test the significance of each component. So analysis of variance mean we partition the variance into different components. This is due to fertilizer effect. This is due to water effect. This variability is due to nutrient effect. Likewise, variance observed from the data partition into different component using this ANOVA. Then we can test whether component from each variable is significant or not. Use ANOVA table to partition the total sums of square into different components. So ANOVA can be used to compare more than two treatment means. First, we need to familiarize with the notation. Consider the measured live weight of goat from an experiment with 3 treatments. These treatments are denoted as T1, T2, and T3. And 4 replicates. We have 4 replicates in this experiment. Those are denoted as R1, that is replicate 1, R2, replicate 2, R3, replicate 3, and R4, replicate 4. Here, these are the result of this experiment. Here, these are my treatment T1, T2, T3. Then these are my replicate. First replicate, second replicate, third replicate, and fourth replicate. You can see this data outcome or weight is not same. Those are different. There is a variability. There is a variability among these observation. This one is 16, this one is 21, this one is 18, this one is 13. Here we have applied same treatment to these 4 animals, but readings are different. Readings are different. So there is a variability among observation. Here also variability. If we consider this total variability of observation, we can divide this total variation into 2 parts. That is within treatment variation. Here, this variation is within these treatments. We call within group variation. And this variation here, here to here, here to here, this variation we called as between treatment variation or between group variation. So from ANOVA, what we can do is this total variation of the observation can be divided into 2 groups as within treatment variation and between treatment variation. This is the within treatment variation. This is the between treatment variation. So, after doing statistical test, if we recognize that this between treatment variation is greater than this within treatment variation, that means there is a significant treatment effect. This between treatment variation has increased due to that treatment effect. Consider if we apply same treatment here. This one also T1, this one also T1. So this total observed variation, again we are dividing into two parts as within treatment variation and between treatment variation. Then you can see this between treatment variation also similar to within treatment variation, because here there is no differences among these treatment. We applied same treatment here and here also. So between treatment variation equal to within treatment variation, then we can conclude that there is no treatment effect. If between treatment variation is greater than within treatment variation, then we can conclude that these treatments are different. So, we need to understand some notation. I think in statistics, most difficult thing is to understand the notation. As you already know, we denote dependent variable using English letters. We use subscript to identify the source of observation. That is, from which observation particular data is coming, from which source particular data is coming. For example, observed value of dependent variable, that is y, it may be yield, weight or anything, in the first treatment and first replicate, we can denote it as y11. So y11 denote the treatment number. This denote the replicate number. In earlier example, here first treatment, first replicate value is 16. So y11 is 16. So y12 is 21. Similarly, here y34 is 25. So here y11 representing that data point is belong to first treatment and first replicate. So any observation from this data set, I can denote as yij. Here I represent treatment number and J represent replicate number. So when I equal to 1 and J equal to 1, it refers to first observation. When I equal to 1, J equal to 2, it refers to second replicate of first treatment. Likewise, assume we want to denote the total. This total of first treatment, total of first treatment. So here I can denote total of first treatment as Y, that is the first treatment. That is first treatment. So I am using 1 there and dot. Y1 dot. So that dot indicate the total. Dot indicate the total. 1 indicate the first treatment. So Y1 dot mean first treatment total. So similarly, Y2 dot mean second treatment total. And Y3 dot mean third treatment total. If we want to represent the replicates total, this is the first replicate. Here, 16, 19, 24. If we sum up these three observations, it will be belong to first replicate and it will be the first replicate total. If we want to denote that total, first replicates total, I can write as y in the place of treatment, it is dot, because that value is not belong to anything. Dot and 1. That means first replicate total. Second replicate total y dot 2. Third replicate total. So here, this is the first treatment, first replicate value. This is the first treatment, second replicate value. This is the first treatment, earth replicate value. This is the second treatment, first replicate value. Second treatment, second replicate value. Likewise, second treatment, earth replicate value. Likewise, we can have t number of treatment. So this is the tth treatment, first replicate value. This is the tth treatment, second replicate value. This is the tth treatment, earth replicate value. So if I total all these observations, that total is the treatment 1 total. Treatment 1 total. So that total belong to treatment 1. Therefore, I am using subscript 1, and it is not belong to any replicate. It is the total of those replicate. So here I put the dot. So Y1 dot means first treatment total. Similarly, Y2 dot mean second treatment total. Likewise, YT dot mean teeth treatment total. Teeth treatment total. So, likewise, first replicate total can be represented using Y dot 1. Second replicate total Y dot 2. Third replicate total as Y dot R. And grand total as Y dot dot. That representing this grand total comes from all the treatment and all the replicate. Then total variation or total sums of square. You know is the sum of the square deviation of each observation from grand mean. So the formula to calculate the grand total can be written as summation yij minus y dot bar square. Here you know y dot is representing the grand total of the data set and bar representing the average. So this means average of all the data that we call as a grand average. So total sums of square is calculated as deviation. First you have to calculate the deviation of each observation from their grand mean, then square those deviation and take the summation. Using shortcut formula, you can calculate total sums of square as summation yij square. That means yij represent or any observation. Ith observation, ith treatment, jth observation. So that is any observation. So here meaning you have to square all the observation in the data set and take the summation of those squared observation. Then from that total, you have to deduct the square of grand total divided by number of observation in the data set. We will do example, then you will understand. Here, this is our data set. We have 3 treatments and 4 replicates. If we calculate the square each and every observation, and here 16, first observation, that is y11, square that. Then this is 21, that is y12, square that. Likewise, you have to square each and every observation here. Last observation is y34. It is belong to third treatment, fourth replicate. This is y34. Square that. Then take the summation at those squared observation. That will be equal to 4918. Then, according to our formula, now we have find this part as 4980. This part. Now we want to find this part. In order to find this part, y dot mean grand total. You need to find out the grand total first. Grand total mean observation, sum of each observation. You have to add 16, 21, 18, 13, likewise 25. When you add these things, you will get grand total y dot. It is equal to 240. Now you can calculate the total sums of square of this data set using our formula, that is summation, that is summation yij square minus y dot square divided by n. This is the summation yij square, this part, that is 4980. Then y dot is 240. Then square it and divide by number of observation, 12. Here 12 observation. Then when you solve this one, you will get the 118 which is the total sums of square of this data set, total sums of square. Now we have calculated total sums of square of this data set. As we discussed, we can divide this total sums of square into two parts. That is between treatment variation and within treatment variation. So we will see how to calculate between treatment variation, also known as treatment variation or treatment sums of square. Treatment sums of square is the sums of squared deviation. Sums of squared deviation of each treatment means from grand mean. Here, we can calculate the each treatment mean here. This is from this data set, we can calculate the first treatment mean. That is this 4 observation, add up and divide by 4. Then it will be here treatment mean. Likewise, you can calculate the second treatment mean here and third treatment mean here. Then you will have 3 treatments means there. That is y1 dot bar, y2 dot bar and y3 dot bar. So treatment variation mean you can find also grand mean y dot dot bar. That is the grand average of all these observations. So treatment sums of square mean you have to find variability between this grand average and each treatment mean. Grand average and each treatment mean. That refers to treatment sums of square or treatment variability. So you have one mean for treatment 1, that is y1 dot bar. Another mean for second treatment, that is y2 dot bar. Another mean for third treatment, that is y3 dot bar. Then when you average all of these 12 observations, you will get the grand average. We represent it as y dot dot bar. So this treatment mean will be differ from this grand average. Second treatment mean also will differ from grand average. But treatment mean also will differ from this grand average. So there is a variability between treatment means and grand means. Treatment means and grand mean. Treatment mean and grand mean. So this variability we refer as treatment variability. Treatment variability or between treatment variability or between groups variability. So we have a formula to calculate this between treatment variability. We use this formula to calculate the total variability of this observation. We have another formula to calculate this between treatment variability. That formula is summation yi dot bar minus y dot dot bar. Square everything and take that squared total. That is here what you have to do, as I explained, first you have to find out the average of each treatment. First treatment average, second treatment average, third treatment average. Then find the grand average of the data set, grand mean. That is total sum of total number of observation divided by number of observation. Then you have grand average and each treatment average. Then find the deviation of each treatment average from grand average. and square those deviations and get the summation. And we have to multiply those by number of replicate in order to equally weight. I will explain that later why we need to multiply by R. As a shortcut, you can remember total sums of square. Total sums of square, we calculate it as summation yij minus y dot bar square. We wrote this as a shortcut as summation yij square minus y dot square divided by n. This is the shortcut formula which is equivalent to this formula. Similarly, we can write equivalent formula to this one. It is a shortcut of this formula, that is the summation yi dot square divided by r minus y dot square divided by n. You can see here we have common thing, that is this part. This part is common for total variation finding formula as well as sums of treatment variation finding formula. We call this part as the correction factor. We call this part as the correction factor. So in our experiment, total number of observation n is 12, which is comprises of t number of treatments, that is 3 treatments, and r number of replicates, that is 3 into 4 is 12 here, n is 12. So I wrote that expansion there. Here, this one you can calculate by adding these total, first treatment total and square it. Second treatment total, square it. Third treatment total, square it. Then take the summation of those squared total and divide by number of replicate, that is 4r. Then you know how to find this one. Here, add all the observation, that will be equal to y dot. Then square those total, that is 240 square, divided by number of observation, that is 12 t into r. Total of first treatment is 68, total of second treatment is 80, total of third treatment is 90. So first we have to find this total, then square those totals, then divide by number of replicate. Here we have 4 replicate for each treatment. Thus divide by 4 and get the summation. That is equal to 4872. So earlier we identified total variability of this observation as 180. Now total treatment variability or between treatment variation or between group variation is 72. Here in our formula to calculate the treatment sums of square, we have summation yi dot square divided by r minus correction factor, that is y dot square divided by t R, T into R. So this part is 4872. This part is 4800. This part, and then by deducting this, by this we can get the treatment sums of square, which is 72. Now you can see we calculated total sums of square of this data set as 118, and part of variability. From this, we identify as treatment variation or between group variability. It we calculated as 72. So total, from this total variability 118, we identified this between treatment variability is 72. So this part is within treatment variability. We know this total variability comprises of between treatment variability and within treatment variability. We know the total variability now 118, between treatment variability as 72, then within treatment variability is 46. So this is the ANOVA does. ANOVA partition this total variability into different component. First component we identified as treatment variability or between group variability, that is 72, and within treatment variability is 46. Now we can test whether this treatment variability is significantly larger than this error variability. Here, this within treatment variability we called as error variability and also as residual or error variation. Okay, then we figure out total sums of square and treatment sums of square, or total sums of square and between group variability. As we know, total variability is equal to within group variability plus between group variability, or we also call within treatment variability as residual or error. So sums of square error you can find by deducting treatment sums of square from the total sums of square. This pie chart shows the partition of total variation as between treatment variation and within treatment variation. So 72 is between treatment variation and 46 is within treatment variation of residual. So this data we got from a sample, that is we use only 12 animals. So this variability we calculated using this sample data. We don't know what is the situation in the population of this treatment. So in order to test whether in population also this within treatment variation is between treatment variation is larger than the within treatment variation, we have to do a statistical test. That test used to compare two variability we call as F-test. F-test. In F-test, what is doing? It is testing whether this between sample variation or between group variation is larger than this within group variability. In this case, you can see this variation is large than this within variability. In this case, you can see these are the between group means. Between group means these are less variable than this within variability, within group variability. So F-test is used to compare two variability. If calculated value is computed by dividing variation of between treatment dividing variation of within treatment. This statistics distributed as F distribution with if there are B number of groups we used to compute this between treatment variability, then degrees of freedom B minus 1 and residual degrees of freedom, residual degrees of freedom. We will see how to find those degrees of freedom. Here, we have three groups. So, degrees of freedom for between group variability is 3 minus 1 equal to 2. Then total degrees of freedom is total number of observation minus 1. Here we have 12 observation. So 12 minus 1 equal to 11. That is the total degrees of freedom. Here what we need is residual degrees of freedom is total degrees of freedom minus treatment degrees of freedom. So 11 minus 2 equal to 9 is the residual degrees of freedom. So in order to find the critical value for this test, you have to find the table value of F corresponding to 2 and 9. 2 and 9. This is the F table. Here in this first row, it is giving the degrees of freedom of numerator. That is when we constructing F value, calculated value for numerator, we put the within treatment between treatment variability, and so from this first row we have to find the degrees of freedom related to between treatment variability, that is 2. And in the denominator, we put within treatment variability or residual. So in this first column, you have to identify the degrees of freedom related to residual. That is 9 in our example. So critical value for this test is 4.26. If our calculated F value greater than this 4.26, we can reject our null hypothesis. So our null hypothesis for this test is all treatment means are same. We write it as mu1 equal mu2 equal mu t. That means null hypothesis is treatment 1 mean equal to treatment 2 mean equal to treatment 3 mean. As alternative, we can say alternative hypothesis at least mean of one treatment is different. So depending on the value we obtain for the test, table value is 4.26, calculated value 72 divided by 2 divided by 46 divided by 9. This is equal to 36 divided by 5.1, which is equal to 5 point something. 5 point something. This is greater than our 4.28 table value. Therefore, we can conclude our null hypothesis is rejected. Null hypothesis is rejected. That means at least one treatment is different from other treatments. So, in order to formally easily do this analysis, we are organizing this calculation into a table. We call that table as ANOVA table, analysis of variance table. In the analysis of variance table, we have columns and rows. First column represent the source of variability. Second column represent the sums of square. Third column represent the degrees of freedom. Fourth column represent the means, sums of square. Fifth one represent the F calculated value. F calculated value. So we can identify in this data set total variation we partition into two, between group variation and within group variation. So under source we have three rows now, one for total, one for within group variation, one for between group variation. Then sums of squares, we calculated sums of square using those formulas. Total sums of square was 118, and between sums of square was 72, within sums of square was 46. Then here between 72 within 46 total 180. Now degrees of freedom as we calculated, we had three groups. So t equal to 3, 3 minus 1 is 2, 2. So between sample degrees of freedom is 2, and total we had 12 observation. Then 12 minus 1 is 11, total degree of freedom is 11. Then within sample degree of freedom is 11 minus 2 is 9. Then mean sums of square. Mean sums of square mean sums of square. Sums of square between sums of square divided by their degree of freedom. Within sums of square divided by their degree of freedom. Here, then 72 divided by 2 here. 72 divided by 2 equal to 36. Here it is 36. Here within sums of square divided by their degree of freedom. It is 46. 46 divided by 9 equal to 5 point something. Then if calculated value computed as sums of square between sums of square between mean sums of square, this one, between mean sums of square divided by within mean sums of square. So that is, this is the 36. 36 divided by 5 point something here. 36 divided by this value 5.11. So this will be the calculated F value. So here we have sums of square calculated for between sample variability. Here sums of square calculated for within sample variability. This is total sums of square. Then here we have degree of freedom, total degree of freedom, treatment degree of freedom, or between degree of freedom. This is within degree of freedom or residual degree of freedom. Then this sums of square divided by degree of freedom, you can get the mean sums of square. Mean sums of square here. Then this within sums of square divided by their degree of freedom, you can get mean sums of square of the within within mean sums of square within. Then mean sums of square between divided by mean sums of square within, we can get the F calculated value. So if this F calculated value is larger than the F table value, we can say there is a treatment effect, or between group variation is larger than within group variation.